Hello, welcome to the course on diffraction techniques in materials engineering. Today, we are going to begin a new topic of discussion on reciprocal lattice. You may recall we have extensively discussed about the crystal structure, symmetry, and the 14 Bravais lattice. Whatever discussion we have made, they all are in real space. Now, how this particular crystal or a unit cell will look like if we simply visualize a reciprocal space. There are couple of reasons why we need to consider a unit cell in a reciprocal space. But before going to those discussions, we first need to recapitulate some of the mathematical ideas or formulas to visualize and to understand the reciprocal space. And then when we will consider a unit cell in a reciprocal space or a lattice in a reciprocal space, that is the reciprocal lattice, it will be very much interesting. And all these understanding on the reciprocal lattice or reciprocal space are very well linked with the diffraction, whether it is an electron diffraction or it is an X-ray diffraction. Those things we are going to learn step by step. So let us begin today's discussion. So, a crystal could be defined with some unit vector, and these vectors are known as the crystal unit vector. Which are represented by A1, A2 and A3. Now, very similar way, we can define a reciprocal lattice vector as B1, B2 and B3. Now, we first need to find out what is the relation between this A1 crystal unit vector and B1 reciprocal lattice vector. So, B1 is equal to the volume V of the unit cell into A2 cross A3. Similarly, B2 is equal to 1 by V into A3 cross A1, and B3 is equal to 1 by V, V is the volume of the cell, into A1 into A2. So, if we simply consider a triclinic unit cell, then we can simply draw this A1 vector, okay, A2 vector, and A3 vector is in this direction. So let me complete this cell. A1 vector is OA, OB is A2 vector, so from A3 vector along the C-axis we can simply draw a perpendicular. This angle is perpendicular, so this is OP, because at the end we need to estimate the V. V is the volume of the triclinic unit cell. So now you can easily see that B3, what we wrote earlier, that A1 cross A2 divided by V. So A1 and A2 is basically the area of the parallelogram. Divided by the area of the parallelogram multiplied by, this parallelogram has the area what I am talking about, O, A, C and B. That is basically the area we are talking about, multiplied by the height. Here height is represented by OP, okay, height is represented by OP of the unit cell. Well, if that is the case, then we can again write it in this way, that 1 by OP, because this area and this area goes out, so only 1 by OP. Now what is this meaning of 1 by OP? OP is represented by a particular plane, and you can easily guess the plane. That is actually 0, 0, 1 plane. So OP basically means that 1 by D of interplanar spacing of 0, 0, 1 plane, right? So we could correlate the reciprocal lattice vector B3 with the particular D001. Now if we recall our school days understanding on this particular vector multiplication, then it will be easier. Here we have learned that A dot B is equal to AB cos alpha and A dot B is equal to B dot A. The schematic representation of this particular can be understood with this A vector, and here let's assume this is origin, this is B vector, and this is actually the angle alpha in between them. So if I draw a perpendicular line from the end of this A vector, and this is basically the angle 90 degree, or otherwise from B we can also draw a perpendicular line. So the scalar product of the two vectors are represented in this way. Okay. Now, very similar way we can try to visualize the cross product. The cross product basically means C is A cross B, or A into B sine alpha. How it happen? Because similar way, if I draw the A vector and B vector, this is vector B, and so the angle is alpha, so C is equal to A cross B, and here actually this A cross B is correlated with a negative sign into B cross A. And I hope this particular understanding is well known by all of you. Now, if that is basically the case, then I can again call those earlier calculation what I have just shown you, that very similar way, that B1 will be 1 by D into 100, or B2 should be 1 by D of 010, right? And definitely B3 is equal to 1 by D001. This we have already derived earlier and proved earlier. Now let us try to visualize the situation once again with the help of some schematic. Now whatever I am going to draw, this drawing is in a two-dimensional plane. So here let's assume this is a point of the origin, and this one is the A1 vector, right? Whenever I call this vector A1, you immediately should interpret in this way that this is in a real space. Here is the A2, and A3 vector is basically perpendicular to the plane where A1 and A2 are lying. Therefore, I cannot show it to you, and since this particular vector is passing through the origin, I write here A3. Well, if that is the case, then I can visualize many different planes from here. How? So this particular plane is 100 plane, and this one is a 010 plane, and if I simply join this end, then the plane is 110 plane, or if I simply join this plane, okay, then this plane should be 210. So the Miller indices in the real space, we have learned a lot. But the same way, it will be interesting to learn in the reciprocal space. Therefore, I will again draw the same and try to represent those planes in a reciprocal space. So this is 0, 0, 0, the origin, and here is the B1. Whenever I call this B1, it basically means it is in a reciprocal space. Well, so here we basically call this B2. Now if I draw these planes, then this particular one unit, so 1, 0, 0, isn't it? Now here this is 1 unit, so this is 0, 1, 0. Okay, so what is this particular? It must be 1, 1, 0, isn't it? We call it as H110. Now this particular point in the reciprocal space is 2, 1, 0, because in the B1 vector I have 2 unit and 1 unit here. I can again draw a particular vector of H, which will be 2, 1, 0. Okay, so this particular point here, it is 0, 2, 0. This one is 1, 2, 0. Here it is 2, 2, 0. So a vector that is capital H, small hkl. Now we are talking about actually a reciprocal space. A vector that is capital H, then small hkl, that is drawn from the origin of the reciprocal lattice. You can see here I have drawn H, capital H 110 and capital H 210. So I represent in general HKL, capital H HKL, that is drawn from the origin of the reciprocal lattice. So how to represent this capital H? So this is capital H, small hkl. That can be represented with small h into B1 vector. B1 is in the reciprocal space. K into B2 plus L into B3. The very same way as we represent in the real space. Well, so how much should be the length of the vector? Yes, that is very interesting. The length of the vector capital H, small khl, that is represented with this half arrow on the top, is equal to the reciprocal of the spacing of D HKL. What I want to mean that capital H small HKL should be 1 by D. D is in the real space HKL. Or maybe it is better to write in a blue color in the real space. So the vector that we have drawn B1, B2, I can also write here B3 because B3 is basically the perpendicular to this particular plane where B1 and B2 are existing or lying. Well, so what do we learn out of it? That the B3 vector is perpendicular to both A1 and A2. A1 and A2 are in the real space. So B3 into A1 should be equal to B3 into A2. How much it should be? Please have a look at the scalar product. There it is written cos. So cos alpha means cos 90 degree. You must know. That will be is equal to 0. So B3 and A3, if we simply put a dot product B3 into A3 is equal to B3 into the projection of A3 on B3. That is basically the understanding what we have. So that will be is equal to 1 by OP into OP. It will be 1. I am referring to a figure where I have shown you this particular OP vector. Here I am talking about this particular vector. Okay, so to generalize this, it will be interesting to write that AM and BN, B is in the reciprocal space, A is in the real space, should be always 1 when M is equal to N. There is no doubt. Or if it will be 0 when M is not equal to N. So this is, let's say, a relatively generalization of this principle. Now we are going to look at the vector additions. Once again, I draw here the A1 vector and A2 vector and the A3 vector. Now please remember that whatever I am drawing here, is in the real space. Whenever I talk about A1, A2 and A3, they all are in the real space. Well, if that is the case, then the plane that I am going to draw through A, here this particular small A1 is basically in the direction. So a point that has a Miller indices of A1 by H. Very same way I have B. So B basically means that A2 by K, and I have C. Okay, C basically means A3 by L. So I can simply draw a plane through ABC. Now from the origin O, I can draw a direction, and that direction will be in such a way that it will make a perpendicular to ABC plane. Okay, because the plane here is H, K and L. I mean, that is represented by A1 by H, A2 by K and A3 by L. The unit vector here, that is actually the N, towards a direction of capital H. This is small n. So how to correlate this A1 by H, A2 by K and A3 by L? To understand this, we need to begin this calculation through the vector addition. Well, here please have a look. A1 by H, this vector plus AB is another vector here, AB. A1 by H plus AB vector is equal to A2 by K. No problem with that. Okay. So now AB is equal to A2 by K minus A1 by H. So if I now make a scalar product of H into AB, please remember AB vector is lying on a plane of ABC, that is that HKL plane. I am multiplying with H. H is perpendicular to ABC plane. So the result is known to us. And H is basically the direction which is equal to H B1 plus K B2. Please look at our earlier derivation. B3 multiplied by A2 by K minus A1 by H. This value will be is equal to 0 because the H vector that is perpendicular to ABC plane. Now further to continue this, please remember that H direction, capital H, that must be normal to AB and AC. That is for sure. So the reciprocal relation between italics capital H, please remember this italics capital H and capital H are different, and D is basically the interplanar spacing. So the reciprocal relation between capital H italics and the D that we are trying to find it out. And here n, small n, is a unit vector that I repetitively told you earlier in the direction of capital H. That is actually the normal to the H scale plane. So if that is the case, then the interplanar spacing what we are talking about is basically ON. Please look at this figure. Here the N is the point where the direction capital H cut or meet on the ABC plane, that is here. That is the point. And the unit vector is small n. So D, that is the interplanar spacing, is ON, is equal to A1 by H, that vector we already understood, and multiplied by small n. This is not H. H is here. And here the italics H is basically is in the reciprocal space. Now small n is basically is equal to that capital H by italics capital H. Or otherwise we can write that D is equal to A1 by H multiplied by capital H by italics H. Once again, we all know what is the value of capital H. That is actually HB1 plus KB2 plus LB3, right? And this italics H represent actually the magnitude of the scalar in the reciprocal space. The italics H represent the magnitude of the scalar in the reciprocal space. So what will happen? The value what we wrote here, that will be is equal to 1 by italics H. So what we have started with, we proved that D is equal to 1 by italics H, nothing else. So this is all about the vector addition. So today we have learned the vector addition and a very brief and very first impression of the reciprocal lattice or reciprocal space. Here how we do the vector addition or in a cross, I mean the scalar, or let's say the cross product or the dot product. And we also try to look at a simple two-dimensional lattice, how they look into the real space and also in the reciprocal space. We will continue the discussion in the next class. Thank you.